Astronomy Cast, episode 281 from Monday, November 19th, 2012. Explosions in Space. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville. Happy Thanksgiving, Pamela.
Happy Thursday in Canada.
Exactly. Thanksgiving already happened a long time ago. But you know what's really weird is we're getting Black Friday in Canada now.
You are?
Yeah, so we're all of our stores and stuff are now doing Black Friday events, but it doesn't mean anything. What is this Black Friday thing? I mean, Canadians all know because we see Americans go crazy every year for shopping, but we had never had sales that were called Black Friday and Cyber Monday, and now this is the first year. Clearly, there's some kind of conspiracy. They're all getting together and doing it. So
we've hit the time. You bought something?
I bought a new lens for my camera thanks to the upcoming Black Friday. I bought a new 50mm lens for my camera, a nifty 50. So, cool. All right. So, are you ready to talk? Oh, just a reminder to everybody that this is we record these episodes of Astronomy Cast as a live Google Plus Hangout. We do this every Monday at noon. In theory, although we're not doing it on Monday, but normally we do it on Monday. So if you want to watch us record live, ask questions, see what we look like, you can do that. All right, let's get rolling. All right, and now today's episode actually was a suggestion from a reader. This was from a listener, and I don't remember the person's name, but someone's like, "Oh, I want to hear explosions in space." So we both thought that was a cool idea, so we're doing it. All right, so we've all seen the classic science fiction space explosions full of flames and loud sounds. Beautiful on the screen, but totally lacking in any kind of science. What's wrong with science fiction? What would chemical and nuclear explosions really look like? What would we hear? And what are some natural explosions that nature detonates in space? All right, so let's just sort of dismantle sort of a TV science fiction trope. You got this, like Star Wars or Star Trek, and you've got, one spaceship shooting its rockets at the other spaceship, and the rockets hit the hull, and you get these explosions with flames, coming out, and
going to sort of happen if you hit the fuel
sound.
Yeah, no.
Right? So what's wrong?
Well, what isn't wrong, I think, is a more valuable question. So first of all, anytime you have explosion, you need two things. You need a fuel and you need an oxidizer. And this is where we mix multiple chemicals and rockets. It's where, when we have solid propellant, it's a mixture of chemicals. It's why the Hindenburg exploded so beautifully, is it had just a little bit too much, it just wanted to go because of that fuel to oxidizer mix. Now, in space, you don't have air, so you have to bring your own oxidizer with you. In space, you don't have the air pressure that comes with the air, which we don't think of as being important in explosions, but those are part of what moderate the speed at which explosions take place. So if you imagine blowing up something on a bonfire. So you take, don't do this, I don't recommend this, but should you choose to, if you take a rocket engine from a model rocket,
should a very bad person decide to throw a rocket engine into a fire,
it will go kablooey. Yeah. And that's in part because you have the air pressure holding in the rapidly expanding explosion. So it slows it down to a velocity at which you can see the explosion taking place. And it also, that rocket engine does have its own fuel and oxidizer. So here all we're talking about is the kablooey part is moderated by having that atmospheric pressure on it. Now, if instead of looking at a rocket engine, you are a truly bad person, you decide to blow up, say, a nuclear weapon in the Earth's atmosphere.
Or in a bonfire.
I don't think the the nuclear weapon would happily sit on the bonfire going, I'm a nuclear weapon.
Yeah, but sure, you detonate a nuclear weapon, yeah.
Yeah, so should you go through all the steps necessary to purposely explode a nuclear weapon in the Earth's atmosphere? all of the energy released in that explosion is going to cause the Earth's atmosphere to fluoresce. It's going to create shockwaves to the atmosphere. It's going to create all of these clouds that we're used to. But all of this is generated because the atmosphere is there. Now, you take away that atmosphere, and you go into outer space with that rocket engine, and you find some way to detonate it because there's not going to be a bonfire in outer space. Well, that rocket engine is going to poof in fractions of a second you probably won't see, entirely combust, and it's going to give off light. It may give off shrapnel. All of it is going to expand in perfect sphere, assuming it's a spherical explosion. Now, admittedly, rocket engines are cylinders, so it'll probably be a cylindrical explosion. But nonetheless, it'll be an expanding explosion that's over like that, because there's nothing to confine the explosion. Just phew, done. Except you won't hear the phew noise I made with my mouth.
Of course. We'll get to that in a second. Right, so I guess the point being, though, that, if you had like a balloon filled with hydrogen, and you tried to light that on fire, without any oxidizer, it wouldn't work. Right, unless you could, somehow turn your balloon into the size of a star, and then it would, then you could have some fusion reactions going. But if you
that's slightly different.
Yeah, but if you hit an electric spark to this balloon, nothing would happen. You would pop the balloon, and the hydrogen gas would escape because there's no oxidizer to make the explosion happen.
Right.
But with a rocket engine, or maybe with gunpowder, with dynamite, with a bullet, the oxidizer is contained within the explosive itself, right?
So that's part of the mixture that they use for many of these different things. Now, the interesting thing when we look at spacecraft exploding is there's this always billowing flame.
Yeah.
And you only get that while the ship's atmosphere is escaping, and that's going to be an extraordinarily rapid process. And if you've ever gone past some sort of a refinery at night, you may have seen at the top of the giant columns that they have for processing things, sometimes if they have excess gas, they'll burn it at the top. Well, what you have the potential of seeing is if you get a very, very small hole and there's too much oxygen in the air mix, and we're pretty good about not doing that. We learned that lesson during the Apollo era. But if there's too much oxygen in the mix, you can end up with a flame coming off as the oxygen burns up. But you need a fuel to be burning as well. So you've taken and put a cylinder of fuel on, and and that's not going to happen. That's not how you attack things in space. So mostly you simply get it explodes, things fly apart, it's done in fractions of a second. Not exciting.
Okay. No, but I mean, things like a gun, for example, would work in space.
Yeah, totally.
Yeah.
Well, it depends on the mixture that you use, because not all gunpowder is made the same.
Right, but the point being that the oxidizer is inside the bullet.
As long as inside the bullet doesn't matter. I'm trying to remember how modern bullets work. I'm just going to shut up. I don't know how modern bullets work. I just know how a Civil War era ones that they taught us, where you put the stuff in, drop the bullet in, and
right. Well, right. So it's the same thing. It's all it's caseless. You've got the bottom part of the bullet, and in that is the gunpowder, and the gunpowder contains the oxidizer, and then it shoots out the the little bullety part.
Then you're good. Then you're good. As
but
long
a
as
stick of dynamite,
oxidizer.
right? Like a stick of dynamite would work, but if you tried to light the fuse, that wouldn't work.
No, would not work.
You would need some kind of
candles,
some kind of detonator, right? Okay, so that's sort of the first part. So whether or not the thing's even going to explode is one question.
Right.
Then the question is, what is going to happen from the expansion, the kind of, as you mentioned, right? That let's say these missiles, these chemical missiles, crash into the Battlestar Galactica, right? and they're going to be able to explode, and there would be atmosphere inside the spaceship, for example.
Right.
But you're going to get shrapnel coming out, but you're not going to necessarily get these gouts of flames unless there's additional fuel inside the spaceship that lighting on
So
fire.
the giant explosion myth, just get rid of it. What you can end up with is much more of a peeling apart type of an event. Sort of like if you imagine a torpedo hitting a ship. No one, when they think of a torpedo hitting a ship, is really worried about flames rushing out the side of the ship. When you hit a spacecraft, you're going to end up deforming that part of the hull. If you break through, you're going to end up puncturing that part of the hull. And normally the hull evenly supports the pressure against it from the inside atmosphere. Now, if you create a weak point in the hull can end up bowing out from the pressure inside, has now found a weak point, and that weak point is just going to shred open. This is sort of like if you've ever had a bad blue jean experience, that one small hole in the knee ends up soon your entire knee is exposed. That same thing can happen to a ship. Now, there's probably not going to be the flameage. There's probably not going to be the giant expanding cloud of glowing plasma material, because really, where's all that stuff coming from?
Right. So I'm just trying to think of what you would see, right? You'd see this
Shrapnel.
missile coming in. Yeah, exactly. You'd see this missile
shrapnel.
coming in. It would pierce the hull. You would see a bright flash of the explosion, and then you would see whatever was left.
Yeah.
So you would, as 1 millisecond later, after the flash went away, you would see the damage, and the damage would be, a gaping hole on the side of the ship.
And it might take time for the ship's deformation to continue to take place as things weaken. We've all watched something slowly fall apart, and that's possible, where it takes time for the stresses on the system to shred the internal scaffolding of spacecraft. But that's what you're looking at is basically the air pressure inside and the structural integrity of the spacecraft falling apart.
Now let's talk about the sound. Right. Let's talk about the sound, which is that other piece of the puzzle, which again, every now and then some movie director bravely tries to make it soundless, right?
And humans don't like that.
And people don't like that. That just isn't right. I think they did it in the new Star Trek movie, where you could see it was the outside of the ship.
And Battlestar Galactica did it sometimes.
Yeah. But even then, they're just like, okay, people hate this. We got to put in sound. So what would really happen? So I'm on my ship. I'm whatever. I'm even like 100 meters away from your ship.
100 meters is a pretty good distance for a small explosion.
Well, that's what I'm thinking, yeah.
Yeah. So what ends up happening is all the energy from that explosion spreads out in a sphere. So there's what's called a 1/r² law. Yeah. So every time you double your distance from where the explosion took place, the amount of energy that's going to whack you goes down by a factor of 4.
And I highly recommend people watch Mythbusters. They do some really great like high speed video of it, they slow it down, slow motion of these explosions. You can actually see that expanding, the expanding shockwave as it's leaving the explosion, and that's the thing that's gonna, if you're close enough, that's gonna hit you, right?
Now, for a small explosion, that shockwave is not going to contain within itself enough energy to do very much unless you're very, very close. And if you are very, very close, then it might be just a thwack on your hull, and you hear the basically the escaping gas whomping you. But beyond that shockwave hitting you, there's no source of noise.
Right.
And so anytime you hear noise in space, if you hear explosions, that's probably your own spacecraft, and the noise is transferring through the hull and through the air in your spacecraft. Other than that, you're not going to hear explosions.
Right, but you're not going to get that explosion of, in the atmosphere, you've got the shockwave, which sweeps by in a thousandth of a second, and then right after that, you've got the air molecules bumping into each other, dispersing the energy from the explosion.
Well, so you have the light goes past you first.
Yeah.
Then you have the sound wave hits you. That's the main shock wave, and after that, it's just dissipating heat.
But so really all you're going to get is that pressure wave, but the pressure wave has no medium to move through, right?
Well, so in space, it's no longer the same sort of a pressure wave. In space, you have the material that was confined and whatever exploded moving out, and so it's it's not pushing with it all of the air molecules, which is where you don't get it carried as far as you do here on Earth. Instead, what you get is whatever was here is now here. And it's that expanding material that's going to hit you. But it's the material that was tied up in the explosion, not the whole sphere of expanding gas that got superheated by the explosion.
Now, with an explosion here on Earth, even if you're, depending on the how powerful the explosion is, and if you're roughly close to the explosion, you're going to get hit by that pressure wave, that shock wave, and you can very well just get killed by it. It's not going to, the energy isn't going to work the same way when it's out in space, right? I mean,
no, and I mean that's the thing, is you really need to be an exploding star before you have enough energy to do something like that. It's the energy very quickly dissipates. It just, there isn't the atmosphere to take in the energy and then impart the force on your body.
Right. So we've got that example, that first example of like a chemical rocket shoots in silently. You see a bright flash, and then you see some wreckage. You see some damage on the ship from what it struck and exploded.
And even a nuclear weapon.
Well, and that's my next question, right? So with a nuclear weapon, what would we see?
The exact same thing, but faster. So you'd actually see less of it, because your brain just can't register what's happening, because there is no atmosphere to fluoresce. And so it's just this flash of energy. And the thing with a nuclear weapon, unlike a conventional weapon, is it is going to vaporize everything that made up the original weapon. And so when you detonate that nuclear weapon in space, it's a flash and you're done.
It's gone. Yeah.
And you probably won't even see very much of the flash, because the majority of the light is given off in wavelengths we don't see with our eyes.
And it's given off at light speed, right? But the point is, like, when you've got a nuclear explosion in the atmosphere, you're seeing not just
you're seeing the atmosphere fluoresce.
You're seeing the atmosphere fluoresce. You're
seeing
reflections off of things. You're seeing things heat up, and so out in space that won't happen. So you'll just be suddenly blinded, or if you've got your sunglasses on, you will have registered a really bright flash and be gone, and then whatever was hit by the explosion is also gone.
Yeah.
And that's that. So how damaging would a nuclear weapon be to a spaceship?
Well, it's all a matter of how big is the spacecraft versus how big is the nuclear weapon. So that's always going to be true. But since you don't have the shock waves, since you don't have the fluorescing atmosphere, you're basically looking at destroying the structural integrity of the spaceship. Right. And there's not going to be the after effects of fire and things like that. So in the grand scheme of things, might as well go with a conventional weapon, but the difference is you can pack much more energy into a smaller volume using a nuclear weapon.
Also some really wonderful radiation. You could
really but in space, it really doesn't matter, because your spacecraft's been destroyed. The fact that it's now nuclear and destroyed.
Well, if you're a little further away and you want to just irradiate them, that's all. But
yeah, but space already has that problem. We call them coronal mass ejections.
So right. So I think we've kind of put to bed, I think here, what science fiction says about explosions, and then what reality says about explosions. And I hope it really would make for I wish somebody would do it, but it also would be
such a lame movie.
It would be so boring. Yeah, exactly. Flash, and then actually it would be probably easy from an animation standpoint or whatever, because all you got to do is just have quick flash, and then you've got a torn apart piece of spacecraft. You don't need to animate the in between.
It would be something so. What do they call that French cuisine where your entire meal is like 2 peas and a beautiful piece of carrot? Whatever they call that type of French cuisine, it would be that style of a movie.
Right. It would be very quick, very small. Yeah, and you wouldn't have to make any sound design either. This would be good.
Right.
We're making science fiction.
Silent and beautiful.
So, all right. So let's talk about some natural explosions in space. Some stuff that can really get
much more
the kinds
interesting.
Of the kind of output that I think people are really hoping for. Let's talk about something like the. What are some examples of some natural explosions that people can see?
I think that the most interesting one we've seen within our lifetime locally is when Shoemaker-Levy 9 hit Jupiter. It caused planet-sized explosions, and that was a matter of you had all of the kinetic energy of this impacting group of fragments hitting Jupiter, which the force was enough to cause chemical reactions. There's plenty of oxidizer in the atmosphere, and whoo, and I don't know why I make sound effects. It's natural.
No.
We've been
It was
trained to make
silent.
the sound
Would have been
effects.
quiet.
Well, unless you were in the atmosphere of Jupiter, because the atmosphere of Jupiter would have quite happily propagated the sound effects. So yeah, these giant expanding balls of superheated gas undergoing chemical reactions that led to the emission of light. That's the fancy scientific way of saying the sucker exploded.
Yeah.
So there you get massive compression leads to chemical reactions, leads to exothermic reactions that give off light, heat, expanding gas due to the ideal gas laws, all of these things. It's high school physics writ planet-sized, and it's just awesome.
If you could have gotten really close enough to sort of see what was really going on, because all we saw in the pictures was these black splotches on the surface of Jupiter. But if you could have seen it, would you have seen like a mushroom cloud? Would you have seen right after the bright flash?
Well, the mushroom cloud is a manifestation of how the atmosphere shapes explosions. It's the models that I saw. It was just like flamethrower out the side of Jupiter. Right. So I'm good with that model because that's just your expanding gas expanding into the areas of lower density.
Okay. Well, let's go. You actually hinted at this before. Let's talk about coronal mass ejections, because that's kind of an explosion coming from the sun.
It's an energy release. Another way to say explosion is energy release.
Yeah.
And with our sun, it will get these magnetic loops that are filled with plasma, contain huge amounts of energy. And when the magnetic coils decide to reconnect in different places or just plain break, all of the plasma and energy tied up in that magnetic loop gets released, and it sprays out into space, and you get this shock wave of light moving through first. Then behind that you get variable speed particles that come, and when a lot of these particles hit our Earth's atmosphere, this is when we see the northern and southern lights. And this is beautiful is the only way to describe it. The Solar Dynamic Orbiter, Camilla the chicken's favorite spacecraft, SDO has taken spectacular videos of these things happening. And as our sun moves to being more and more active in the next year, we'll probably get to see more examples of these, and this is going to be the first time we've had a spacecraft this capable of high-resolution imaging, watching all of this energy getting released into space.
So here's my idea for a science fiction story. You tell me how you like this. They're battling around the atmosphere of a star, and one captain tricks the other captain into parking their spaceship right along one of those magnetic field lines. And then,
no captain's that stupid.
Yeah, and then predicting that that's where a coronal mass ejection is going to happen. You're going to get this massive release of energy, and it's going to destroy their.
Well, so the thing is, we're used to looking at still images of coronal mass not coronal mass loops, of magnetic field lines, and the reality is when you look at the movies on SDO, it's like watching a water park except like plasma. It's what our brain interprets as flame flowing through loops, and it's moving, and it's dynamic, and it's awesome, and it would be much more like trying to dodge the flames in hell if you tried to fly your spacecraft through it.
But if you could see some big magnetic field line and predict that a coronal mass ejection was about to happen, you could.
Well, if you were that good, I wouldn't say any parking should be involved. I would say take the barnstormers approach. If you fly your spacecraft through the coronal loop,
time it.
And these things are planet scaled. So like we don't have a sense of scale. We imagine them being Enterprise starship sized, and they're not. This is more like fly the Death Star through it with room to spare.
Yeah. Okay, so now the classic example of an explosion, of course, is the supernova.
Of course. And this is just a matter of giant nuclear bomb in a lot of ways. it's take a star. It could be a white dwarf that has been accreting matter. It could be a neutron star that's been accreting matter, although a neutron star would be a recycled supernovae. Take just a regular, everyday, overly large star that has all of its own mass. And if the center of the star is not pushing out with sufficient light pressure to support the outer atmosphere, then that outer atmosphere can come crashing in. And as it crashes in, as that material compresses, this is the same idea as behind a nuclear weapon. With a nuclear weapon, they use shaped explosives to smush, for lack of a better term, all of the isotopes inside the nuclear weapon together, and that causes fission reactions which release huge amounts of energy. Fusion reactions which release huge amounts of energy. Now, with a collapsing star, you end up with the exact same situation. With your classic giant star explodes, you go through millions of years of hydrogen, helium, carbon, nitrogen, oxygen, silicon, all the way up through ending up with an iron core. Once you have that iron core, you can no longer fuse two atoms together and through the fusion process produce energy that then holds out the outer part of the star. When you get to that point, no more light getting produced to support the star. Star collapses. You then end up with the atoms getting compressed to the point that they break apart. Energy is given off in the breaking apart stage, and it's kind of violent.
It blows my daughter's mind that that all of the gold in our house was formed in that moment that a supernova went off.
Well, and it's one of these things where the universe, prior to having enough supernova going off, wasn't actually capable of supporting the creation of planets like Earth. We could not have formed much earlier in the universe unless we were in just the right location near where a supernova had gone off. It's taken billions of years for all of the content from so many generations of supernova to sufficiently mix to create galaxies like our own that are just filled with planets.
Now, a hypernova, that's just a flavor of supernova, right?
It's just a giant one that has magnetic fields that trigger gamma ray bursts.
And a gamma ray burst is the biggest.
A hypernova.
Hypernova, yeah.
It's what you see when you're pointed along the beamed energy.
Right.
It's a
Which
geometric
again,
effect.
some clever captain, after ruining one spaceship from a coronal mass ejection, then flies the spaceship through the potential beam of a gamma ray burst, and then
we can't predict those well enough.
No.
And really, anywhere within a few thousand light years, and you're crispy.
I know. Exactly. So leads them on a merry chase into the left half of the galaxy, right? at which point a gamma ray burst goes off and destroys the entire half of a galaxy. So yeah.
That doesn't actually happen. I love the fervor with which you destroy physics. It's really quite awesome.
No. If you are half a galaxy away and you are in the beam, then zap. That's all I'm saying.
It doesn't destroy planets. It doesn't destroy half the galaxy. It might destroy your atmosphere.
That's right. It wipes out. And
it's 7,000. It's 7,000 light years is the danger zone, and galaxies are like 180,000 light years. So it's a much smaller fraction than half.
Right, but if you get hit by the beam directly. But yeah, no. You know what's a good book for this is
Phil
Death
Plates.
from the Skies by Phil Plait. Yeah, highly recommend.
Yeah,
it'll show you all the ways that the universe is trying to kill you.
And we have a poster. You can buy our poster for Christmas. It's an awesome poster.
I'm actually wearing the shirt right now.
We might be out of stock on the shirts. I think we did a limited edition run.
Cool. We should do a color version of those shirts. They're really cool. All right. Well, you know what? I think we've clearly reached the natural ending. But I would love to see people email us suggestions of maybe the best possible explosion they've ever seen. So what is the best space science fiction
explosion? So we're not real explosions.
Not real, although real ones are great too. But the best science fiction explosion you've ever seen. Who has handled it the best? There's some YouTube clip. Just drop us an email, info@astronomycast.com. We'd love to sort of see them and see if we can find the one that we like best. And I'll post it to Google Plus or mention it in a future episode. That would be really cool. Okay, well, thank you very much, Pamela. And have a good Thanksgiving.
Husband's Canadian. We're ignoring it the way you are.
Oh, perfect. That would be best. All right. We'll see you later.
Fine.
Stop. Save. 1 second, folks.
Whoa. Yes. I almost quit the Hangout instead of stopping the recording. It's one of those days.
All that matters is the recording, the safety of the recording.
Yeah.
Export. Save. Done. All right.
Where.
Yeah, somebody mentioned that I told the internet that I have gold certified. Yes, I do. I have a gold wedding ring. Ooh. Okay. So like I said, so we'll stick around now for a little bit of time, and we'll talk about take some questions from people.
Sounds good.
Let's see. I guess someone wanted to know about the Project Orion,
Yeah.
the nuclear explosions that get detonated behind a spacecraft. What's actually going on there, sort of physics-wise?
It's just the pressure from the explosion when you're up close and personal still can do harm.
And so, but I guess the point being that they've got like a big blast plate, and they're dropping these nuclear bombs.
Yeah.
Everyone's ever heard of this, right? Project Orion is this crazy idea to build like a skyscraper-sized spaceship, and it would pack it with like 1,000 nuclear bombs, and then
and it's not the most effective way to move things.
no, but very flashy. So you drop these nuclear bombs behind the spacecraft, and then you detonate them, and they hit.
I'm not sure it's so much dropping them as pooping them.
Pooping them, sure, and they hit this blast plate on the back of the spaceship, and then that propels the spaceship faster and faster because the shockwave from a nuclear explosion moves so quickly, you can get a really high velocity on your spaceship. But it's crazy to drop all these nuclear bombs behind you. But I guess the point being that you're not going to get, as we talked about, right? You're not going to get shrapnel. You're not going to get shockwaves moving through air.
The thing is, it's not efficient. Ion drives are the most efficient way to do it because with a nuclear weapon, you have a sphere of expanding energy, and the only energy that's going to matter to you is the part of the sphere that is hitting your spacecraft and then moving in the exact opposite direction.
But if you really have
all
to
the rest
get there
of the energy
now,
you build one heck of an ion drive and don't take very much weight.
I wonder how far you could take that. I mean, could you build an ion drive so powerful that it could get off the Earth?
Get off the Earth now because they don't accelerate fast enough. You need to use conventional something to get off the planet. But at a certain level, the technologies that are along those lines, and railguns are along those lines, where you're using magnetic fields to accelerate things in a linear direction. You can use a railgun to launch things into orbit in theory, and there's rumors kicking around that the military has figured this out, or Canada has figured this out. I love it when it's the military or Canada. Yeah. So with railguns, it's the exact same physical principles as an ion drive. You take something, use a magnetic field to accelerate it, and you spit it out one direction, and conservation of momentum spits you in the other direction. With a railgun to launch something into space, clearly you're going to need something different once you get into space to keep you going. but it's the physics works.
I've wondered about, there's these ideas of really high altitude balloons that you could build, these like kilometer-sized balloons, and have a little payload and take it right up to the outer reaches of the atmosphere. And I wonder if you could have that plus an ion drive. So once you get this spaceship like really high up, and so there's almost no atmosphere at all, you're like 100 kilometers up.
Like they've done with Camilla the chicken.
Way further than that, though. A much bigger balloon, right?
Okay.
So Camilla, you got her to say 30 kilometers, like what happened to Felix Baumgartner, right? But take it way further than that with a much bigger balloon. And people have been talking about this, using it as a waypoint for going into space. And could you then have an ion drive from that point and
I
start to accelerate around the Earth, because you're buoyant, but you need to have that side momentum, but you're not going to get slowed down by the atmosphere so much anymore. You could slowly sort of
Yeah, you're
spiral
making it
outward.
way too hard. Sometimes you just use chemical explosives. It's fine. That's the
I
most
don't want
efficient way
chemical
to get
explosives.
going.
All right. So Dex Lusso wants to know if I record standing up. I do.
You do almost everything standing up.
I do everything standing up. Yeah, but we have a saying in the information technology business: so whoever sits most dies first.
Yeah.
So
My
yeah,
my
so
husband actually, he for a while had an extremely expensive stand-up desk because he'd done so much harm to his back sitting at his keyboard.
yeah, so I try to sit down to do work as little as humanly possible, like when I'm tired of standing. But yeah, mostly I stand. Um, Minor Glitch 01 wants to know, how would an explosion differ on Earth, Mars, and the Moon?
Um, Earth, we've seen. Mars would be a wussier version. Moon would look like space.
So when you say wussier, so if you took like a a,
There's just not
a
that
piece of
much
dynamite and
atmosphere. So you'd
detonated
have
it,
all the effects, but they'd be so for instance, if you exploded a nuclear bomb in the atmosphere of Mars at a low altitude, you would get the ghost version of that beautiful explosion that you see on Earth, because there'd still be atmosphere to fluoresce, but it would be much, much thinner. So it would be like the old style ghost photography where you take two exposures and you superimpose the one. So you'd have that fluorescing, but it would be much more transparent.
hmm, I wonder. So if you were near a big block of C4, would you take more or less damage? I wonder.
Less.
You take less damage because there's, I guess, because you have less air getting compressed,
Right,
and that
exactly.
compression wave isn't going to hit you as hard.
Right.
Right. Okay. Um, Scott Lewis is recommending Firefly,
Yes, I love
but they
Firefly.
didn't they break down at some point. I know they did some of the space battles, but I recall them being one of the shows that did them that gave
They
up.
did so few episodes. I know Battlestar Galactica gave up periodically,
Yeah.
or goofed
Yeah.
up. I'm not sure which. Um, but I think Firefly stayed true.
hmm
But this may just be me being a Whedon fangirl.
Oh, this is something completely different. Mike Justice asks, what is a black dwarf, which we've talked about.
A very cold white dwarf.
Right. So a white dwarf is the burnt out cinder of
Yeah.
a star that's cooling down, and a black dwarf is actually, I guess, a theoretical object that will exist when the white dwarf has cooled down to the background temperature of the
Yeah.
universe. Like,
And we found cooled off white dwarfs. That's the awesome thing, is we know that all of the theories behind the idea of using white dwarfs as cosmic chronometers to measure the age of things by knowing the temperature they had when they formed and observing the temperature they're at now, we can see that cooling trend.
yeah,
And so they are going to slowly fade from these blue-white objects down through the red, out into the infrared to the cold.
yeah, and eventually it will just be a blob of carbon, a diamond, really, the
Well,
same
they come in
temperature
a
as the.
variety of different compositions, but yeah.
Yeah, yeah,
And so then it just becomes a matter of, do protons decay or not? And if protons decay, eventually they just decay. And
yeah.
that's depressing.
Probably get sucked into a black hole first.
And black holes don't wander around seeking things out. So as long as they're in a stable orbit, they're fine.
Um, Let me see. So Carolyn McCardle asks, why does our atmosphere produce a mushroom cloud-shaped explosion, where we mentioned that the explosion on Jupiter only produced a jet shape?
So I have to admit, I don't know all of the complexities of the Earth's atmosphere, but it does have to do with the effects of different atmospheres having different pressures and temperatures,
But
and
also
I
it's
just don't know the details of it.
right, but I think it's the source of the explosion, right? In this case, you've got a comet impacting the atmosphere of Jupiter, and then all of that mass and kinetic energy being turned
But
into the
it gets
explosion.
turned into an explosion that's still a spherical explosion.
Right,
But
but in with a nuclear weapon in the Earth's atmosphere, it's not the kinetic energy. It's you're just
It's
detonating
it's
it.
just but in both cases you end up with that spherical release of energy unless it's a shaped nuclear weapon, and I don't know if you can shape a nuclear weapon.
No,
Just
but
don't know enough about
no,
them.
I know, but like at any angle that a
Yeah,
contrastor is coming in, it's always going to produce pretty much the same crater, right?
but the big difference is with the explosion on Jupiter, you have a much lower pressure where we're seeing that fountain of flame coming out, and so you have this expanding cone that has an end point, that and it's that's creating the
Yeah.
fountain of flame.
So here's a good question. So Desislava Jaliva asks, how do you feel towards the Death Star explosions in Star Wars?
Oh man, I need to rewatch those.
Well, if you recall, they, go through the little trench, and then they shoot their little rocket shuttle,
Yeah.
and it
So
goes
the
down
big
in, and it hits the reactor, and then the thing detonates like a supernova.
and so the big question is, was it what fuel did they have on board? What oxygen did they have on board? Yes, it was way too big of an explosion. It was simply way too big of an explosion.
Right.
But
Well,
but yeah, it's a moon-sized
what
object. So
if the power source of the Death Star
uh-huh.
was a, let me think, a black hole
No.
a
No.
white dwarf
No.
surrounded by enough material to heat the Chandrasekhar limit,
Yeah,
and then
no.
around that is the Death Star.
No, that would have been way too much mass to try and manipulate the
It's
spacecraft.
a moon-sized object. How big
It
is a
doesn't
white
matter.
dwarf?
It's a moon-sized object, but the amount of energy necessary to steer that bastard, you're not going to
No,
get.
no. You take a white dwarf, okay, and then you surround that white dwarf with zero point 0.4 white dwarf's mass of material,
Gravity
and
doesn't
then
work that
and
way.
then you drop it into your white dwarf, and then you put your Death
Yeah,
Star around that.
physics does not allow
And
you
so
to do
then
that.
the rocket goes in, it hits the thing that's stopping all that mass from hitting the white
You are
dwarf.
making up
No,
non-physical
I'm not.
scenarios.
I'm, oh, right, like the Death Star is a physical scenario. I'm just
There is the ability to construct a Death Star. It's easier to hollow a
right.
moon than build a moon,
So
but
the bottom line here is that if you actually uh, somehow blew up the reactor, like all you're going to do is somehow create some kind of structural weakness, and it's going to kind of deform a little and kind of tear itself apart through its own
and
gravity.
the way you would have ended up with any sort of massive explosion is you can imagine that instead of having a crazy white dwarf in the center, it had a giant tokamak reactor, some sort of a nuclear reactor in the center, and that's what you would need to have
But
the
even if you
ability
had a
to.
nuclear reactor, you're not going. Okay, hold on. Antimatter. What if it's got a massive antimatter fuel source in the middle of the Death Star, and then you hit it with your rocket, which is the same amount, and then you're going to get that explosion.
Yeah, it that I'm willing to go with
Okay.
antimatter. I'm
All
willing to
right.
go with
All right.
nuclear. I'm not willing to go with white dwarf. Yeah, so with a antimatter reactor, assuming that you had a significant amount of antimatter. I mean, we have antimatter going through us
Mm-hmm.
all the time, and we just ignore it.
Right.
But if you have a massive amount of antimatter capable of reacting with the matter of the spacecraft, you can end up with a vast energy release. But again, that's flash o' light, not billowing gassy explosion. So it's the billowing gassy explosion. If they manage to hit a bunch of pure oxygen tanks, so you can imagine that it has like Manhattan skyscraper-sized oxygen tanks, and
Yeah.
those are going off because
Right.
they were liquid oxygen tanks.
Sure.
That's the only way you're going to get that sort of
Right.
billowy
That
random.
there's that the right. But the point is, I think the only feasible way is if it's got a massive antimatter containment field in the middle that is containing the fuel to run it for a couple of decades, and then that containment field gets breached, and
Collapsed.
the antimatter spins out and collides with the matter of the spacecraft, and you would get a big explosion. But you wouldn't get that exact explosion, but
Right.
that would be a lot of energy. But I guess the question is, and this is where the math comes in, would it be enough to like make it go kaboom and
Oh
just
yeah, yeah,
into tiny little pieces? Like it was there, and then there was no Death Star anymore.
yeah.
So how much antimatter would it take to make a Death Star's worth of metal vaporize?
Probably a house-sized amount of
Could you do
antimatter.
the math, please? We'll wait.
Not right now, no.
But you could.
I could do the math. I'm not going to
Nice.
do it today. I'm going to go ride my
Nice.
horse today. That is my
All
goal.
right. Well, that's okay. You can submit it within a couple of days. The viewers won't mind. Um, all right, but that we've decided that that's the only way that the Death Star had to have been powered by an antimatter system and an awful lot of antimatter. Um, somebody wants to know. Oh, somebody was mentioning that, in fact, the electromagnetic pulse from a nuclear explosion is quite devastating as well, which is, I think, a good point.
But the 1 over r squared, it's still, you have to be pretty close for it to bug you. And space distances, it's pretty close, doesn't happen very often.
So somebody mentioned if you're going to Yaroslav Rabovoluk says, in conclusion, if you're going to blast someone in space, use frag grenades.
Yeah.
Or more importantly, just throw metal at them at high velocities.
Yeah,
Like,
Battlestar Galactica totally got this right. Use high speed projectiles.
yeah.
Bullets.
Yeah.
Bullets work.
Bullets are just great because one tiny little bullet breach is going to let your atmosphere out.
Yeah.
So by all means, just throw pieces of metal at your enemy ship. And if they're moving towards you and your bullets are moving towards them, it's going to cause a lot of damage. And the thing is that nothing's going to stop them. There's no really gravity to pull them away. There's no atmosphere to slow them down. They're just going to keep moving forever. So,
yeah.
Cool.
Yeah,
right,
we have to worry about spare. You just made me realize we have to worry about like loose bullets in space
from space battles.
Yeah,
half a galaxy away.
Right, exactly. Well, not half. By then, hopefully, stars would have vacuumed all the spare bullets. But yeah, this is like one of those crazy. That's actually a concern.
No, it's not. No, it's not. You won't let me
stray bullets.
You won't let me park a white dwarf inside a spaceship. I will not let you worry about bullets from a space battle.
Well, if there's ever a giant intergalactic or interstar system war, it will be just like the mines that get left behind after ground-based wars. Instead of random mines, it will be stray bullets still continuing to move. It's not like they fall to the ground and get lost in the dirt like they do here on Earth.
All right. Well, there's your NaNoWriMo plan for this for next year. Is that how you say it?
Yeah, NaNoWriMo.
NaNoWriMo, yeah.
Yeah.
Whew. I actually like these parts after because we get to be a little more silly about the regular listeners of Astronomy Cast have no idea the madcap schemes that we get up to after the regular show is done. All right, well, I think we should probably wrap this up. So we're going to do our next episode on Monday.
Yeah.
Will you be holidaying on Monday?
No.
No? Okay.
No.
Cool. All right. Well, then we'll be so noon Pacific Monday. We'll do the next episode.
Sounds good.
I have no idea what we'll be doing. I sent you 50 topics, so you should be good for a year. Cool. All right. Great. Well, thank you very much, Pamela, and thanks to everybody watching. We're going to be doing the virtual star party on Sunday night, so if you want to join us then, that'll be great. Where we hook up a bunch of telescopes live into a Google Plus Hangout and show you what the night sky looks like. So thanks, everybody. We'll see you guys all later.
Bye-bye.